Okay, so here we go. 5.4, number 6. So your drawing is this. I always do that with my pulleys, so deal with it. My pulley's in the wrong spot. All right, so here's what it tells us. It tells us that block A has a mass of 10 kilograms. It tells us that it's on an incline, which is at 35 degrees. It tells us that the coefficient of static friction is 0.4. It says an attached string is parallel to the incline and passes over a massless, frictionless pulley at the top. The largest mass, MB, attached to the dangling end for which block A remains at rest is something. All right? So, did you have an idea about how to start this one, Cam?
Well, I just started by putting in the forces on.
Okay, cool. So what do you got? So, get me started.
Okay, so is it 35 degrees?
Yeah, it's 35 degrees.
So then, the gravity perpendicular would be.
Are you figuring it out right now? Anybody have those written down?
I don't have it down. Well, that one would be 80.3.
80.3?
Yeah.
Which means my normal force is also going to be 80.3, right?
Yeah, then I think the parallel is 46.1.
46.1 newtons. Cool. All right. Everybody good up to there? Okay, what else? There's one other thing, well, two other things I should do almost as just knee-jerk. Sure, what do you got, Tubba?
I mean, you can put the friction.
Friction. So talk to me about friction.
So I'm putting it to the left, right?
Oh,
Yeah. So
I don't know.
Pulling to the left.
Okay, good. So how do we know friction has to be pulling to the left here?
Is this?
We're trying to maximize this mass, right? We want as much mass as possible, but we don't want it to move. So if we're maximizing the mass, that means that the system would move this way if it weren't for friction. So Sabo, you're exactly right. Our friction has got to go this way. What kind of friction? Static. And because we're trying to maximize the mass, we also want to maximize the static friction, right? So let's do that. Force of friction static max is our normal force times our coefficient. So 0.4 times 80.3 is going to give us, 32 or 0.12 or something like that? 11 or 12 newtons. Everybody good up to there? Cam, you good up to there?
Yeah.
All right. So what else?
M2, M2.
Good. We've also got this force here, right? Which would be MB times G, right? Everybody good? Cam, you good? Sarah, you guys, what's up? Talk to me.
Why do we know friction is going down there?
So we're trying to put as much mass as here as we can. We want mass B to be as massive as possible, right? And eventually, if this mass gets big enough, it'll move that way, right? Good. And so friction's going to resist that. Everybody good?
Would you use static friction because that's one of the point where it's starting?
Good. Margaret just asked a really good question. Even though the problem, we're trying to prevent it from moving. So we're going to use static friction. And this sort of represents the breaking point between moving and not moving, right? Everybody good with that?
Yeah.
All right. Cam, are you good up to here?
Yeah.
Do you see where to go?
Well, so if it's at rest and the acceleration 0, is the force of tension equal to the gravity of parallel plus friction or no?
Yes.
Just like the opposite of those two added together?
Yeah. But I think I wouldn't even consider tension in this problem, to be honest with you.
So, is the mass of, the force of gravity on B then equal to?
Yeah, so I guess what I would do is I would start by considering this whole system, right?
Yeah.
Which now I've started coloring it, I gotta finish it. All right, so there's my system, right? And so there's only 3 external forces, right? Gravity, parallel gravity, and friction. And those forces have to add up to 0, right? So, I'm going to go net force equals net force. 0 equals Fg parallel plus Ffk plus the force of gravity on object B. So 0 equals negative 46.1 minus 32.12 plus mass of B times G, right? And then just solve. Cam, does that make sense?
Yeah.
Sebo, you good? Everybody good? All right, now, I guess it turns out that you could think about tension. Because what is if the system is not moving, then what does the tension have to equal? Not numerically, but letterically.
MBG.
MBG, right? Look, if it's not moving, then the tension has to be enough to make the net force on B 0, right? So the tension has got to be equal to the force of gravity on B. Okay? So weirdly, if you solve this problem for object A, you get the exact same equation, right? Sebo?
How'd you get 46.1?
It was the parallel component of gravity. So 9.8 times the sine of 35. Times the mass, sorry. Is that not what it is?
No, that's 56. I got 56.
Oh, wait.
I got 56.
I got 56.1.
56?
Oh, maybe that.
Somebody lied to me. Let's see. 98 times the sine of 35. I agree, 56.
Who lied?
All right.
Why don't you leave yourself being serious?
Sorry about that. All right, are we good? Cam, are you good?
Yes.
Is everybody good?
Yes.
Is anybody ungood?
Let's do some more.
Okay. How would this problem change if I asked for, well, A, would it make sense to ask for the minimum mass?
No. Wait.
Well, the static friction would still keep it from
Yeah, you can still do it.
Yeah, so if the mass gets smaller and smaller, eventually the system will go the other way, right? So how would that change my drawing? What do you got, Justin?
You have to have static friction going up the ramp.
Good, you'd have your static friction going up the ramp instead of down the ramp. Follow?